Okay, as we finish up chapter 25, dealing with carboxylic acid derivatives, let's talk a little bit about nitriles. Now, a nitrile is a C triple bond N that's attached to an alkyl group. So that is a alkyl nitrile. The way to make a nitrile is very simply to do an SN2 reaction on a primary or a secondary alkyl halide. So if I take, for instance, a primary alkyl halide and react it with Cn-, which is cyanide, we'll have an SN2 reaction occur, and we will end up substituting the C triple bond N, which is what the Cn- is, and we'll end up forming then our primary, or forming our nitrile attached to a primary carbon. And we could also do this with a secondary carbon, also reacting it with a cyanide ion so that it comes in and does an SN2 reaction. So we can substitute a primary or secondary halide with a nitrile. Now remember that a nitrile undergoes hydrolysis primarily under acidic conditions is how you would do this. But if I took, for instance, my secondary nitrile that I just made and I reacted it with H plus H2O, I would end up then forming the I would end up forming the carboxylic acid. So hydrolyzing the nitrile, and I'll remind you of what that mechanism is, would end up converting then that carbon group to the carboxylic acid. So nitriles by definition are carboxylic acid derivatives because when they undergo the hydrolysis reaction, in this case acidic hydrolysis, they produce carboxylic acids. So that's one way we can use nitriles to make carboxylic acids by simple SN2 reactions. Nitriles how do you make a nitrile? Usually what we use is we just use a cyanide ion in order to add that to an alkyl group like we just did. But there is a way to make a nitrile by doing a dehydration reaction. And so what we can do is we could take, for instance, an amide, so that's our amide, carboxylic acid derivative, and we can treat it with SOCl2, which we normally think that SOCl2 just replaces an OH group with a chlorine, but in this case it's a dehydrating reagent. So what will happen is that we will convert the amide into a C triple bond N. So this is a way to synthesize the nitrile from an amide. Now, in terms of that mechanism, it is kind of outlined in Top Hat, in the Top Hat textbook, but let's just talk a little bit about how that mechanism works. So there is my amide with my lone pair on the nitrogen, which I will talk about later in terms of whether that can be used to bond an H+, and the answer is going to be no, but I'll talk about why. And SOCl2 is simply that. So what happens, and the sulfur has a lone pair and then the oxygen has two lone pairs, because remember sulfur can have an expanded octet. So what happens in this case is this pair of electrons of the nitrogen will move, and then the CO double bond, that pair of electrons can be used to bond the an oxygen-sulfur bond, and then this pair of electrons goes to the oxygen to keep it from violating the octet rule. So what we end up with is, we end up with the O attached to the S, which now has an oxygen with 3 lone pairs on it, and therefore a negative charge. We have a double bond to the nitrogen, which now the nitrogen has a positive charge because it's given up an electron. And then the other 2 things attached to the sulfur are the 2 chlorines. So now what can happen is we can lose a chlorine by bringing this pair of electrons back down from the sulfur-oxygen single bond, kicking off a good leaving group as a chlorine. So we can lose a Cl minus, and then what we're going to end up forming is we're going to end up forming the S double bond O with now a Cl on it. So that sulfur still had its lone pair, and now we have nothing happen to the nitrogen. It's still involved in a double bond with the positive charge. So the chloride basically is not going to act as a strong base. It's going to pick up the proton. So in this case, what's going to happen is I'm going to simply lose this H plus, and the chloride is going to pick it up. So I'm going to end up basically eliminating HCl from this. But it's not so much the chlorine is coming in and grabbing the hydrogen as it's being lost to reestablish that nitrogen, as a N that has a neutral charge. So then as far as the rest of the molecule, it's going to still look like this. But now my nitrogen is going to have its lone pair back. So in essence, I've made a neutral molecule by losing that H plus from the nitrogen. Now, in the final step, what's going to happen is that I'm going to end up losing this H plus from the nitrogen bond, so I'm going to end up forming the triple bond. The OC bond is going to break and go to form an SO double bond, and the chlorine here is going to leave. So I'm going to end up with the carbon-nitrogen triple bond. I'm going to end up with the oxygen doubly bonded to the sulfur, which is doubly bonded to the other oxygen. So in other words, this part of the molecule. And I'm going to end up with a Cl minus, and that Cl minus is going to end up combining with that H plus. And so I'll end up forming then my nitrile by that second step. So what I'm making is I'm making a nitrile by what is called a dehydration reaction. So what I'm ended up doing is I basically am losing H plus, and this is a deceptive name because dehydration usually means you lose water, but I'm not losing any water. So we end up with this reaction to make our C triple bond N from the amide. So this is the first case where SOCl2 has done something different. It is considered a dehydrating reagent because it will readily react with water. Now, the overall driving force of this reaction is the formation of the sulfur dioxide gas. And so as that's formed, it would bubble out of the reaction, and basically there's no reversibility in this case. So that is the way we can prepare nitriles by the dehydration of SOCl2 and an amide. And the amide has to basically have 2 hydrogens attached to that nitrogen. Okay, so I'm going to take a little bit of a detour here and talk a little bit about ester and amide, what's called stabilization, and why we've always protonated the carbonyl oxygen in an ester and an amide and never the oxygen or nitrogen. So if you have, for instance, an ester, whenever we add acid to an ester, you could think, well, why aren't we protonating the oxygen that essentially came from the alcohol in the ester? And the answer is because that oxygen actually has a slightly positive charge to it. And you're like, wait, what do you mean a slightly positive charge? Well, here's a resonance structure that I can draw for an ester. I can take this pair of electrons, move it here, and then move the pair of electrons up to the oxygen. So a legitimate resonance structure that I can draw, okay, it's not very stable, but give me that, is I can form this resonance structure. Now remember that the resonance hybrid is the weighted average of those two, and if this second resonance structure is formed at all, even though it's not really greatly stable, what I'm going to end up doing is forming a partial double bond from the oxygen, the carbonyl group, a partial double bond to the other oxygen, and a delta minus charge on the oxygen of the carbonyl, and a delta positive charge on the ester oxygen that came from the alcohol. And so even if this has the slightest bit of positive charge, the H plus cannot add to it. And so we never add the H plus. The H plus, well, let me draw the arrow in the correct direction. The H plus never gets added to the ester oxygen. We always protonate the carbonyl oxygen. So ester oxygens are not basic because of that second resonance structure. And we can do the same thing for an amide. So if you had an amide with a nitrogen with a hydrogen, let's say an R group here, if I was to add the H plus to that, we would normally think, well, nitrogen is a stronger base than oxygen because remember, CNOF, as we go from right to left, basicity increases. But in this case, I can do the same thing that I just did, which is move the pair of electrons to form a CN double bond and move that pair of electrons up on the oxygen of the carbonyl. So that I can form that resonance structure. And again, not a very stable resonance structure, but if it does form, then that means that the resonance hybrid would have a partial double bonds, a delta minus charge, and then a delta positive charge on the nitrogen. So again, that nitrogen is not able to be protonated. So this is something we haven't talked about, so I want to make sure that we have. So whenever we're protonating esters and amides, we're always going to just protonate the carbonyl oxygen. That's what we do. Okay, and this is the reasoning behind that. Okay. All right, nitrile reactions with Grignard reactions to form ketones. A review. In other words, if I take, let me put some specific groups in here. If I take a nitrile and I add to it, let's say the methyl Grignard, followed by a then H plus H2O step, which always follows a Grignard reaction. What product do I make? I make the ketone, where the alkyl group came from the Grignard. What's the mechanism for that reaction? Again, a review. I'm not going to go through the entire mechanism, but I'll set it up. C- comes in and attacks this carbon. Pair of electrons moves to the nitrogen. The carbon-nitrogen triple bond has a carbon with a delta positive, a nitrogen with a delta minus because the polar covalent bond. And so what I end up doing is I end up adding the methyl group here. I end up with a double bond now with the nitrogen having a negative charge. That's it. Nothing else I can do. I can't bring this pair of electrons back down because there's nothing else, no groups that leave. So I'm stuck. And so what happens? The next thing we do is we add our H plus, H2O, and that's always going to be in excess. And so my N minus is simply going to be protonated. And so I have that compound. What is that called? That's an imine. Are imines stable? Nope, not in acid and water. And so the imine then further reacts with H plus and H2O. And remember, the imine is going to revert back to the ketone and ammonia. And in this case, the ammonia would be protonated by the excess acid, so it would form ammonium. Right? So how did we make imines in the past? We took ketones and reacted them with ammonia, and that gave us the imine. So it just reverses itself to form the ketone. So that's the mechanism. And if you want the full mechanism of how we get from the imine, it's been in past notes. It's really outlined in the Top Hat textbook as well, but it's the same mechanism that I've shown you in the past. Okay, so we can make ketones from the reactions of nitriles and Grignards. Reactions of esters, reductions with dibal to form aldehydes. Okay, so I'm going to take my ester, which again has a carboxylic acid part and an alcohol part. And now what I'm going to do is I'm going to react it with dibal. What is dibal? Dibal is, the B is not there, it's aluminum with a hydrogen with just a completely messed up name, diisobutyl, which is 1, 2, 3, 4. So sorry, diisobutyl. Why won't it erase? So diisobutyl is just this. One, two, three, four. So there's my diisobutyl aluminum hydride, or dibal. There's only one hydrogen here, so that means there's only one H minus. What happens in this mechanism? The H minus attacks the carbonyl, as it always does. I end up with my O minus up here. I've added my hydrogen, and I have now my OR group. That's it. There's just one hydrogen. So now what happens? What happens is this pair of electrons can move back down here, kick off the OR minus group, and let me come back to that in a moment, because you might say, but wait, OR minus is not a great leaving group. It's not. But I'll show you in a moment what really happens, and then I form my aldehyde. And since there was only one hydrogen, dibal cannot reduce the aldehyde, so it basically stays there. So in the reduction of this ester, you end up replacing the OR group here with hydrogen, because the one hydrogen of the dibal. Now you might say, what about this losing this OR minus group? That's pretty unlikely, except it's going to get you're going to get help in this, because what's going to happen is that when I have my O minus up here and my OR group down there, what's going to happen is that O minus, if you take this aluminum hydride molecule and you lose H plus, the counter ion for that is going to be an aluminum, is the diisobutyl aluminum with the plus charge. So what happens is that aluminum can move from being the O minus down here to then basically being the counter ion of the O minus of the R prime group of the alcohol group that's leaving, or it's leaving as an alkoxide, so that when you reform the double bond to form the aldehyde, you end up with the diisobutyl aluminum with its positive charge counterbalancing the alkoxide, and so it ends up stabilizing and allowing the alkoxide to leave. So aluminum does play a role in this, and all these mechanisms are outlined in their gory detail in Top Hat, but that's the reason why we can lose an OR minus group in this case, because of the fact that the aluminum is going to help stabilize it as it leaves. Okay, so that's it. It's not really a new reaction, but the dibal is only has one hydrogen, and so therefore we're going to replace the OR group with an H and make the aldehyde. So this would be a good preparation of an aldehyde from an ester. Okay, next, reactions of carboxylic acid derivatives with Grignard and organolithium reagents. Well, you know, it is true. Because we first started talking about this back when we were first talking about Grignards back at the beginning of the semester. So let's take each one of the carboxylic acid derivatives and talk about what happens when you add a Grignard organolithium reagent to it. Let's go back to, well, let's just take them one at a time. So how about we take the ester? What happens when we react an ester with something like methyl lithium, or this is interchangeable in this class with a methyl magnesium bromide? So what's going to happen is the CH3 minus is going to come in and attack the carbonyl, and the pair of electrons will go up there. So I end up forming then my O minus. I have my OR prime group of the ester, and I just added my methyl group. Okay, what happens next? The O minus brings its pair of electrons back down because the OR minus group can leave. So I end up making the ketone. And this is where we always used two equivalents of Grignard to react with the ester back when we talked about this in in February, because at this point I would get a mixture of products, because once I formed the ketone, if I had some unreacted organolithium or Grignard, it would now go ahead and it would attack the carbonyl of the ketone, so that now I would end up with my O minus, along with my now 2 CH3 groups. The pair of electrons cannot move back down because there's nothing to leave. So this just kind of hangs out and waits to be protonated by H plus H2O. And now I end up forming my tertiary alcohol. And remember, I form a tertiary alcohol where 2 of the groups came from the original Grignard. Okay, so that's the reaction of the ester with the Grignard reagent. Okay, so that's an ester with 2 equivalents of Grignard. Let's do another review reaction. The nitrile with a Grignard or organolithium compound. Let's see how many equivalents do we need here. Actually, we're just going to use 1 equivalent. And the C minus is going to come in, attack the carbonyl. The pair of electrons is going to move to the nitrogen. Now I'm going to end up with an N minus. And let's make the specific group here with the methyl group. What happens next? We talked about this in terms of the reduction of the nitrile. And so nothing's going to happen. The N minus is just going to hang out until it reacts with H plus H2O. And then I'm going to end up making again the imine. There's going to be excess H plus H2O added. So what happens? The imine is unstable. It reacts with the excess H plus H2O. And what do I end up doing? I end up converting that imine back into the ketone. So in the reaction of nitriles with Grignards, which again is a review reaction, we end up adding the alkyl group of the Grignard to form a ketone. You can only do 1 equivalent of that. I didn't say about the acid chloride. Remember, and this would go back to when we originally talked about Grignards as well, I'm going to react 2 equivalents of Grignard with my alkyl halide, so that the first equivalent, with my acid chloride, my first equivalent of CH3 minus adds to the carbonyl. We form a CO minus, and I've got my CH3 group now added. This pair of electrons is going to come back down, kick the chlorine off because it's a good leaving group. I'm going to reform the carbonyl now with the methyl group there, and I ended up losing a Cl minus. Now again, I need 2 equivalents of this because this ketone now will react with another equivalent of organolithium or Grignard, so that I will now end up with my alkoxide with now 2 equivalents of my Grignard methyl group added. At this point, once that second equivalent adds, there's nothing I can do. I just wait for the H plus H2O step to come in, and now I end up forming again my tertiary alcohol where 2 of the groups are the same from the Grignard. Okay, so this was similar to what happened with the ester. So let's see, we got 2 more groups to talk about here. Let's talk about adding the carboxylic acid anhydride with a Grignard. How many equivalents am I going to need with this? So I'm going to add my CH3 minus Li plus to this, or Grignard. the CH3 minus is going to come in and add to one of the carbonyls. If I make this a symmetrical anhydride, it doesn't matter which one I react with. So I'm going to end up with an O minus up here, my methyl group here, my O, C double bond O, R. Pair of electrons can now move back down from the oxygen because the carboxylate's a good leaving group. And so the carboxylate will leave easily. And I will now end up with the ketone. So as we said before, whenever you end up with a ketone, we need two equivalents, because now I'm going to have the second equivalent come in, add to the ketone, and that's going to let me produce the tertiary alkoxide with now two of the groups the same coming from the original Grignard. And then it just waits to be protonated by the H plus H2O to form the now tertiary alcohol. So as you can see, three of those carboxylic acid derivatives, when they react with the Grignard, you need two equivalents of the Grignard in order to make the tertiary alcohol. So you always get the tertiary alcohol when you react it with a either the carboxylic acid chloride, the carboxylic acid anhydride, and the ester. All three of those you're going to react with two equivalents of organolithium or of Grignard, and you're going to always end up adding those two groups to form the tertiary alcohol. The last one is the amide. So let's see what happens when we react an amide with a Grignard. How many equivalents do we need? What's our final product? So now when we're reacting this with an amide, the CH3 minus is going to come in and add to the carbonyl. And what am I going to get? I'm going to get an O minus up here, my methyl group being added there, and then my NHR group. Now, the oxygen can try and bring its pair of electrons back down to form the carbon-oxygen double bond, but that nitrogen being the strongest base, right, in our CNOF, N minus is a much stronger base than oxygen. That means that N minus is going to be a horrible leaving group, and so it's not going to go anywhere. So now I'm going to end up just simply waiting around to add H plus H2O. And when I do that, what am I going to end up doing? Forming the OH with the NHR group, and then adding my CH3 group to that molecule. So what I'm going to do here is, let's see if I can grab this, and I can move it out of the way on my computer. So that's the product that I'm going to make. Wait. I'm using excess. H plus H2O. So what happens next? So what happens next is we add a new slide. Now if you're thinking, wait, maybe I've seen that. Maybe I've seen this before. You actually have. This is called a hemi. It's what I call a hemi-aminal. And it was formed by reacting the amine with the ketone. So what happens? I'll write the gory mechanism of this. the OH comes and gets protonated by the H plus. Although I'm going to be honest with you, which one's going to get protonated? The OH or the NH? Which one's a stronger base? The N is going to be a stronger base, and so the oxygen isn't going to be protonated, the nitrogen is. And so what am I going to end up doing? I'm going to end up forming that ammonium ion, ammonium compound. As we saw with the Hoffman elimination, the ammonium is a great leaving group, so I'm going to break that bond. I'm going to lose that amine, which will now be an NH2R group. I'm going to lose the amine, form that carbocation. Pair of electrons will move like so. I'll end up losing the H plus. And now what did I just make? I just made a ketone. And so think about the reverse reaction. What happened in the reverse reaction? It was the nitrogen that came over here and reacted with the carbonyl. And then we had the H plus go from the N plus to the O minus. So that's the reaction of the Grignard with an amide. You end up making another ketone. And I suppose we should probably talk about, or I should remind you of what happens when the nitrile, which is again our carboxylic acid derivative, what happens with it when it reacts with an organolithium compound. At this point, you could probably tell me the C minus comes in, attacks that carbon, pair of electrons moves to the nitrogen. I now have an N minus. What happens next? React it with H plus. And H2O in excess. What did I just form? Imine. What happens with the imine in excess H plus H2O? See earlier slide. It ends up converting back to the ketone because the amine is unstable. So that's our derivatives reacting with Grignard. Sometimes it takes one equivalent, sometimes it takes two equivalents. So we should think about exactly how many equivalents it will take. Okay, reductions of esters with sodium borohydride or lithium aluminum hydride. If you have an ester and you react it with either sodium borohydride or lithium aluminum hydride, both of those are strong enough to reduce an ester. We would then have our then H plus H2O steps. And what we end up doing in this case is we end up splitting the molecule in half. So this part came from the carboxylic acid in Fischer esterification, for instance. You can think about that as the carboxylic acid half. This is the alcohol half. And this reaction ends up splitting that molecule down so that the carboxylic acid part becomes a primary alcohol and the alcohol part becomes an alcohol. So we end up splitting that molecule in half. And we end up reducing the carboxylic acid part to a primary alcohol. So this is the carboxylic acid part. That's a primary alcohol. Okay. Sodium borohydride will do this reaction. Sometimes textbook will say, no, you need to only use lithium aluminum hydride. I know that an ester will go with sodium borohydride, so that's not an issue. So let's talk about the mechanism of this reaction and how it works. So first of all, I have the ester, and remember there are 4 H minuses that the lithium aluminum hydride can donate. So the first H minus comes into play, attacking the carbonyl and forming the O minus like so. Now the lithium is a counterion for that O minus. And so now what's going to happen is I'm going to be able to bring this pair of electrons back down and kick off the OR group, because it's going to basically form the aldehyde plus I'm going to end up losing the alkoxide as an alkoxide, but the lithium is going to help stabilize that as it's lost. So it's not quite a magic step, but the lithium will help stabilize the OR minus as it leaves. That's going to leave the aldehyde. The second H minus is now going to come in, add to the carbonyl group again of the aldehyde, and I'm going to end up now with an O minus and now adding the 2 hydrogens to the carbonyl group, and I still have my alkoxide over here. So the O minus cannot react further. So now I'm going to wait around for the H plus H2O step to come into play. When the H plus H2O is going to come in and it's going to be in excess, then I'm going to end up protonating the O minus of both the alkoxide and the other alkoxide. So now I'm going to end up with an RCH2OH and the alcohol part of the carboxylic acid. So lithium plays a role in, having done lithium chemistry in my graduate work. Lithium does some special things in terms of being able to stabilize alkoxides. And so it makes this group a much better leaving group. Not a great leaving group, but a much better leaving group than it would normally be. Because normally we'd say O minus is a pretty strong base, therefore a pretty horrible leaving group, but lithium can stabilize that a lot. So either way you look at it, when you reduce esters, you end up splitting them to form primary alcohol on one side and then the other alcohol on the other side. Okay. The reduction of the carboxylic acid with the lithium aluminum hydride. I think we've talked about this reaction before, but let's talk about it a little bit more. If you react lithium aluminum hydride and you need the strongest reducing reagent possible, you're going to end up reducing that carboxylic acid down to the primary alcohol. In terms of this mechanism, the first step will be that, again, there's up to 4 H minuses in lithium aluminum hydride. So the first H minus is simply going to deprotonate. And we're going to end up with an O minus. And we're going to again have a counterion of lithium here. Then the second H minus is going to come in, attach that carbonyl, pair of electrons moves up there. And now I'm going to end up with that species, and again there's a lithium here as the counterion. Now, there is a counterion on the other O-, which is interesting. It turns out that at this point, if you're keeping track of the aluminum H4- has now lost 2 H-. So now it sits here as an aluminum H2+. And that's the magical step in this reaction, because now what I'm going to do, because you're like, how am I going to get rid of one of those oxygens? Here's how I'm going to do it. I'm going to take this pair of electrons to form the carbonyl group, and then this pair of electrons is going to go actually to the oxygen, but it's actually going to go to the oxygen and the aluminum together. So if you think about that species, if I rewrote that, I could rewrite it like this. So it looks more like this. And now what can happen is this pair of electrons moves here, and then this pair of electrons goes to form an oxygen-aluminum double bond. So that what I end up doing is I end up losing the oxygen doubly bonded to the aluminum. It turns out that an aluminum-oxygen bond is really, really strong. So even if you don't like that, think of it this way. Think of it as that. That's what I'm losing. And then I'm reforming down here the carbonyl group. And now my, let's see, now my first deprotonated, my second added. Now my third H- is just going to come in and reduce the aldehyde to now form the primary alkoxide. And now I'm ready for then H plus H2O. It's an awkward mechanism, but it ends up reducing all the way down to the primary alcohol. Okay. So that is that reaction. Hofmann rearrangement of amides to form amines we will talk about in the next lecture, along with the Curtius rearrangement, which is going to actually, the Curtius rearrangement is going to lead us into the next chapter. If you're wondering, all the reactions that we've learned, yeah, all the reactions that we've learned are basically here. These I copied and pasted. There's 3 slides worth of reactions that we've learned, so they're all summarized in the last 3 slides here, which I will keep in. And then what we will do in the next lecture is we will do Hofmann and the Curtius, sort of the Curtius rearrangement and the Hofmann, and then we will move into chapter 26, which is the last chapter of the semester. Yay! So there will be an online quiz for you to do over the reactions that we did in this particular set, and that will be due by 11:30 or by 11:59 in the day that follows where this video goes. So this video is going in on Wednesday. That quiz will be due by 11:59 on Friday.